Right, so thanks very much for the invitation to speak here. So what I really want to talk to you about is some nicely structured determinants that arrive out of moment calculations in random matrix theory that we do. So here, for example, we have a determinant with binomial coefficients. You can see as we go down a row, the top index increases by 1, but as we go across the columns, as we go down a row, the top index increases by 1, but as we go across a column, it jumps by 2 in each column, which makes the determinant a little bit trickier to calculate. Or, for example, determinants like this. So here we have gamma functions. And again, in this case, the argument decreases by 1 as we go down the column, and by 2 as we go over, as we switch columns. And in this case, we have a funny relation between a determinant that looks like this, where we have a jump between the second to last line and the final line. So this one is jumped by 2. And the sort of similar determinant, which has no jump, which just has like continuously increasing arguments, and there's this kind of nifty relation between them. Or maybe like this. So this again is the matrix determinant with these 1 over gamma functions, and this time it looks very nice if you look at this bit. Everything is just increasing or decreasing by 1 as you change columns or rows, except when you get to this half of the matrix, you suddenly find that it sort of started again. So we're back to 1 over gamma 2k, but then you get this funny sort of checkerboard effect with the minus 1s in the second half of the matrix, which again makes it more tricky to calculate the determinant. So I love these calculations where you boil a huge big calculation down to some nice determinant with a nice structure. But I know that not everyone here is as enamored with determinants as I am, so I won't just work through these. I'll give you some motivation as to why we want to study these. So the motivation comes from number theory. In particular,
do you have Q generalizations?
Sorry?
Do you have Q generalizations of these? Where every time you have a binomial coefficient, people write a Q version of it. So you have Q binomial coefficients.
I don't know what that means. I probably know it by a different name. I'm not sure. So the motivation comes from number theory. So the Riemann Zeta function is a function that's very important in number theory. It encodes information about the prime numbers. It can be written as an Euler product over primes, or as a Dirichlet series, so that's the sum over integers. And both of those two expressions converge in this blue bit of the complex plane. So this is the complex S plane. But we can continue those expressions. Well, I have my own, I'll get it out. We can continue those expressions so that we have a function on the whole complex plane, which then has a pole at 1, zeros at the negative even integers, and an infinite number of complex zeros lying in the vertical strip between the real part being 0 and the real part being 1. And of course, the Riemann hypothesis says that those zeros lie, as I've drawn them, exactly on the line where the real part equals a half. The Riemann hypothesis is obviously a very good motivation for doing calculations in mathematics, since it's one of the biggest unsolved problems in mathematics. So there are many ways to approach the Riemann hypothesis. There are many kind of equivalent statements. And so mathematicians have tried to solve it using many different methods. One of these methods involves the derivative of the Riemann zeta function. So this method says that there's an equivalence that says that all the zeros of the zeta function being on this line is equivalent to all the zeros of the derivative of the zeta function being to the right of this line. So over on this side, and if we had no zeros of the derivative of zeta over there, we'd have the Riemann hypothesis. So we have a picture. of the zeros of the zeta function and its derivative. So the green zeros here, so this is the complex plane, there's a half, right? Sort of just, it's a piece of the complex plane. There's a half, the line where the real part equals a half. So these green dots are the zeros of the zeta function, a sum of the zeros of the zeta function, high up on the critical line where the zeros lie. And these blue dots are the zeros of the derivative of zeta. This picture was generated by, there was an undergraduate research project with some of my number theorist friends in the States, and so that was where this picture came from. So we can see, at least as far as this picture goes, the Riemann hypothesis is true. The zeros of zeta are on the half line, the zeros of the derivative of zeta lie to the right of the half line. But we can see that the places where we kind of get into trouble, possibly, is where there are two zeros of zeta very close together, and then the zero of the derivative really sneaks in really close to the critical line. So that's kind of the dangerous spots, right, where it looks like maybe you could get a zero of the derivative sneaking across the line. So because of this equivalence with the Riemann hypothesis, there's a lot of interest in the horizontal distribution of the zeros of the derivative of zeta. So there are some results. So the first one, Levinson and Montgomery in 1974, that the zeta function and the derivative of the zeta function have essentially the same number of zeros to the left of the half line. So the essentially is just because it's an asymptotic result. You go very high up on the critical line, so there are some lower order terms. But essentially, if you found a zero of zeta over to the left of the half line, you'd expect a zero of the derivative in a given interval. And this has allowed number theorists to go a certain way towards proving the Riemann hypothesis. So Levinson in 1974 showed that, so what he showed was that there were less than a third of the zeros of the derivative to the left of the half line, which means that there's less than a third of the zeros of zeta to the left of the half line, from the top statement. But the zeros of zeta come in pairs, one on one side, mirror image on either side of the critical line. So if there's less than a third of the zeros on the left of the half line, there are also less than a third of zeros on the right of the half line, which I think puts more than a third of the zeros of zeta on the half line, which is this result here. And so this is saying like a third of the zeros are on the critical line, where the Riemann hypothesis would put all of them. And then slowly, you can see very slowly, if you look at the years here, that fraction has crept up. So Conry in 1989 has more than 2/5 of the zeros of the zeta function lie on the critical line. A team in 2011, more than 41% of the zeros of zeta lie on the critical line. So the progress is slow, but it is a method that gives you some results in the direction of proving the Riemann hypothesis. So this is to motivate you to believe that studying the zeros of the derivative of zeta is a valuable thing to do. And I'm going to move to talk about zeros of the derivative of zeta. Moments of the derivative of zeta. And so this slide is to convince you that getting bounds on the number of zeros of the derivative to the left of the half line can be related to moment problems, that is, averages of values of the zeta function or its derivative. So here's a picture. Say these green dots are the zeros of some function. This could be any function, but we're going to be thinking of it as zeta primed. So this is a lemma of Littlewood. So essentially, the lemma says if we take the log of some nice analytic function around a rectangle in the complex plane here, then the integral on that contour of the log of your function f is equal to basically the sum of distances from, say, the right-hand edge of your rectangle to any zeros that function has inside your rectangle. So it's relating the integral of the log of f around the rectangle with distances into the zeros of f. And the reason for that is that if we're integrating the log of f and f has zeros, then obviously these are a logarithmic singularity. So we have to have a branch cut going off to this side. So we kind of make our contour go in and tuck around each one of these zeros. And then now, inside this now kind of funny red contour, we have no poles, right? So the integral around this contour of log of f is 0. And so the integral around the rectangle is therefore equal to the sum of the integrals along these little sections here. And it's just it's a logarithmic singularity. So the function on the, say on the bottom of one of these slits is just like 2 pi I greater than the value of the function on the bottom is 2 pi I greater than the value on the top. And so if we look at the difference of the integral of log f along the top with the integral of log f along the bottom, we just have 2 pi I times the length of that slit. And so if you take the real part of that equation, the equation that says the contour integral of log f around the rectangle is essentially equal to the sum of the lengths, 2 pi I times the sum of the lengths of these integrals, and you just take the real part of that expression, then you get this, right? So the log of f has a real part and an imaginary part, and this is what you get if you take the imaginary part of that. Then you get that these are the bits of the contour around the rectangle that are imaginary, and you have your 2 pi I times the distances along these cuts, and so the imaginary part is 2 pi times the distances. So I guess the first thing to say is that, so here on this side we have 2 pi times the sum of the distances from this right-hand edge into the zeros of f. So now say that f was the derivative of the zeta function. This sum of the distances has to be at least as big as the number of zeros lying to the left of the half line times a minus a half, right? Because this distance here is a minus a half. So every time a 0 is on the far side of the half line, we have at least a distance, a minus a half, right? This distance here. And so certainly the sum of all the distances is going to be greater than the sum of those distances for each of the zeros that's on the other side of the half line. Yeah? So it's giving us a bound. So NL is the number of zeros of, say, zeta primed that are on the left of the half line, and so we get a bound on the number of those zeros. So that's essentially the argument. And what we see on this side is that the sort of hard thing to calculate on this side are these averages of log of the absolute value of our function, say log of the absolute value of zeta primed, along these long sides. So here we're integrating from t up to t plus u. So we're integrating some long stretch up the side of the rectangle. And this is the thing that's hard to calculate if f is the derivative of zeta. But so the point is that this expression relates averages of values of zeta primed with a bound on the number of zeros of zeta primed to the left of the half line. So because of that little argument, what number theorists would like to be able to calculate is the average, right, of some stretch. It could be 0 to t, it could be some interval in t, up the half line, so some interval vertically in the complex plane, of zeta primed, its absolute value, and then its log, right? So A is some, maybe it's something a little bit greater than a half, maybe it's like a half plus 1 over log t or something. So we want to find these average values of zeta primed on some vertical line in the complex plane. That's what the number theorists would like to be able to do. This is a hard thing to calculate, and so maybe you could get this average of the log by taking averages of the absolute value of the derivative of zeta, and if you could do that with raised to some power, like a non-integer power, then maybe you could differentiate with respect to that power and set the power equal to 0, and then you could get your log moment. Right? So these are the kind of calculations that number theorists would like to do in order to be able to approach the problem of the Riemann hypothesis.
Question. Are the horizontal integrals easy to do, or are those also challenging?
Like at the top and the bottom of the rectangle. I am told that they're easy to bound and things. I don't know the details, but yeah, according to the number theorists, the hard bits of the long integrals along the sides. Yes. So this is the kind of thing that we want to be able to calculate. So I'm not a number theorist, so I'm not going to tell you how to do this in number theory, but I am going to propose that maybe we could do calculations in random matrix theory, which could help us address questions like this that number theorists are interested in. So let's have a little bit about the connection between the zeta function and random matrix theory. I know this will be familiar to many of you, but maybe not everyone, so let me go through it a little bit. So we've learned over the past many years that we can model the zeta function using random matrices, random unitary matrices. So matrices from UN, n by n unitary matrices. So a particular n by n unitary matrix has eigenvalues on the unit circle, so it looks something like this. So we label the eigenvalues e to the I theta n. So we have the set of all n by n unitary matrices, and we can have Haar measure on that compact set so that we can speak of a random unitary matrix. There are n eigenvalues on the unit circle, and so the density of the eigenvalues is n over 2 pi. The zeros of the zeta function are, well, if the Riemann hypothesis is true, they're points that lie on this vertical line here. The density increases as we go higher up on this half line, and the density increases logarithmically. So it goes like 1 over 2 pi log t over 2 pi. And so the claim is that the eigenvalues of random unitary matrices, which are essentially points on a line, circle, but open it out, it's a line, model the statistical distribution of the zeros of the zeta function, which are probably also points on a line. And so if we want to be able to compare these two sets of points, the distribution of the eigenvalues of the random matrices with the zeros of the zeta function, then we want to scale the unit spacing so that the unit spacing in both cases equal, say is equal to 1, and then we can compare the distribution of these sets of points. So if we scale the Riemann zeros, if those are the Riemann zeros, then we multiply by the density near that zero, and we get a new set of point Wn, which are now scaled to have unit mean spacing. So if we scale the eigenvalues to have unit mean spacing, and we scale the zeros to have unit mean spacing, then we can start to compare statistics. So here's a picture of the nearest neighbor spacing. The dots are the data from the Riemann zeta function. So this is if you take the first 100,000 zeros, so above the point of half, you just collect the heights of the first 100,000 Riemann zeros. And then you calculate the nearest neighbor spacing. So that is, you just take spacings between these scaled, spacing between consecutive scaled Riemann zeros, plot a histogram of those, then you get the dots, yeah? And the solid curve is the nearest neighbor spacing for large unitary matrices. So the spacing of the eigenvalues for large unitary matrices. And then let's go also gathered 10 to the 5 zeros around the 10 to the 12th zero. So this is moving higher up on the critical line and taking a batch of zeros up there. And again, calculated the spacing distribution, spacings between the Riemann zeros. And it shows an even nicer fit to the large unitary matrix results, the eigenvalue spacings of large unitary matrices. And because Elisko does these amazing computations, he has a billion zeros around the 10 to the 16th zero. And when you get up to this point, so we're moving higher on the critical line, and we get up to this point, we see that we have very, very good agreement between the distribution of the zeros of the zeta function and the distribution of eigenvalues of random unitary matrices. And this connection between the distribution of eigenvalues and the distribution of zeros hasn't been proven, but we base a lot of our work on it because we believe it to be true. So there's very good numerical evidence, and there are sort of partial proofs of this connection. So let's assume that this connection holds, that the eigenvalues of random unitary matrices model the distribution of zeros of the zeta function, because that allows us to then go on and use random matrix theory to be useful in number theory. And so to do this, remember what the number theorists want is sort of average values of the zeta function or its derivative. And so we want a function that will take the place of the zeta function, right? In random matrix theory, we want like an analog of the zeta function. And the zeta function is a function with zeros at its zeros, right? And so we want in random matrix theory a function that has zeros at the eigenvalues of the random matrices, because those are the things that have a distribution like the zeros of the zeta function. And so that function will be the characteristic polynomial. So if A is one of our unitary matrices, the characteristic polynomial is defined like this: e to the I theta n are the eigenvalues of A. So this function goes to 0 whenever S hits an eigenvalue of A. And so this characteristic polynomial is going to be what models the zeta function for us. So we want to do kind of analogous calculations in random matrix theory with the characteristic polynomial in order to predict results in number theory about the zeta function. because the density of the zeros and the eigenvalues is different, the behavior of the zeta function changes as we go up the critical line, and we want to know at a given height on the critical line what matrix size do we use to predict the behavior of the zeta function. And the natural thing is to equate these two, the density of the zeros of the zeta function with the density of the eigenvalues of the random matrices. So we get this relation where n is essentially like log t. Right, so now I want to convince you that we can do calculations in random matrix theory that do actually predict real important information in number theory. So we'll address the moments of the zeta function. So this is a calculation from like over 100 years ago now. So this is looking at the average value of the absolute value of zeta. So we're not doing zeta prime now, we're doing zeta. Average value of zeta on the half line, so on this line where its zeros lie. So zeta for half plus it, take the absolute value and square it, and then just perform an average over some interval on the critical line. So this is a result of Hardy and Littlewood, and they got that this grows like log t. So that's like the second moment of zeta. So the fourth moment of zeta, we put an exponent 4 in here. And Ingham in 1926 found that this grows like log t to the fourth. And so these are quantities that number theorists are really interested in calculating. They've been trying to calculate them for over 100 years, but these are the only two moment results that they have proven. So, I mean, number theorists would like to put in the exponent 6, the exponent 8, and so forth, and have all these moments of the zeta function, but these are really, really hard calculations, and so far they're not tractable to methods that we have. So,
can you say why going from 4 to 6 is so hard?
So you can write the zeta function as sums, like Dirichlet sums, and I think the problem is that when the exponent is small, you can kind of take, there are multiple sums, you kind of take diagonal terms, and that when you go to larger exponents, you start having to take more difficult off-diagonal terms that they don't have a way to handle, I think. Right. So what number theorists would like to be able to calculate is this top quantity, so moments of the zeta function raised to some power 2 lambda. Let's say lambda is an integer for now, so even integer moments of the zeta function. And they think that, the structure of these moments is something like this. So A lambda is a product over primes, which number theorists have a form for, so that's kind of maybe an easy bit. They believe it grows like log t to the lambda squared, where lambda is in our exponent here. But then there's this coefficient f lambda, and this is the hard bit to calculate. So this is what the number theorists can't calculate. They believe it's a rational number, but they're only able to calculate that for lambda is 1 and lambda equals 2. So the question is, can we do a calculation of random matrix theory using the characteristic polynomial and use it to predict, to do something about this really hard calculation in number theory? So we want to kind of mimic this moment here. So instead of the zeta function, we take a characteristic polynomial, because that's the function whose zeros has the same distribution as the zeta function. We want to take an average value, we want to raise it to the 2 lambdath power, and then we want to perform an average. And it might look initially that the average you want to perform is the average around the circle, since this one is over the critical line where the zeros lie and the eigenvalues lie in a circle. But in fact, this is a really long average. So it's like taking many, many batches of zeros with statistics like eigenvalues of random matrices. And so the average is sort of over many of these batches of zeros. And so the appropriate average in the random matrix case is to average over all the random matrices, which again is sampling many batches of zeros of random n by n unitary matrix. So this is the appropriate quantity to calculate. And in random matrix theory, that isn't a hard calculation, right? We have Selberg's integral and all sorts of nice tools to do this kind of calculation in random matrix theory. And so this is a theorem in random matrix theory. Here's the behavior when n is large. So n is our matrix size. When it becomes large, this grows like n to the lambda squared, which looks promising, right? Because by equating the density of zeros and eigenvalues, we get n is like log t. And if you replace n with log t, then we have the same growth behavior, so that's good. And we can calculate the leading order coefficient. In fact, we can do this calculation for finite n, so we can get an exact expression. But for the purposes of comparing to zeta, we'll just look at this leading order term. So we know what this leading order coefficient here is. It is indeed a rational number. And the conjecture that John and I made many years ago is that this random matrix coefficient predicts that really hard to calculate number theoretical coefficient. It's a product over primes, which I didn't write down because it's long and complicated, but it's known. So it's a product over prime numbers.
You say the number in number theory they can calculate this a lambda.
Yes, I mean, yeah, they have obviously a conjecture for the form of that a lambda. Yes, so the conjecture is that you can do a fairly easy calculation of random matrix theory and get the answer to a really hard question in number theory. That's what this conjecture says. And this is borne out, in the case when lambda is 1 and 2, which are the cases of known in number theory. There are conjectures when lambda is 3 and 4. And also there've been numerical tests. So we really believe that this is true. That random matrix theory can help you answer hard questions in number theory. Okay, so if I've convinced you of that, then we move back to the question of the derivative of zeta function, right? Average values of the derivative of zeta. So we're hoping that our characteristic polynomials are going to, or derivatives of the characteristic polynomial are going to model derivatives of the zeta function. And if you remember, we had the picture of the zeros of the derivative of zeta, which, at least in the picture, were all lying to the right of the half line. And that is equivalent to the zeros of the derivative of the characteristic polynomial lying inside the unit circle. So we've generated a random n by n, 20 by 20 unitary matrix. There its eigenvalues, the blue dots on the unit circle. So those are the zeros of the characteristic polynomial itself. And then the zeros of the derivative of the characteristic polynomial are these green dots, which lie inside the circle. And it's no surprise that the green dots lie inside the circle, because there's a theorem that says if you have a polynomial, the zeros of the derivative lie inside the convex hull of the zeros of the polynomial itself. So the Riemann hypothesis is true in random matrix theory, kind of without any surprise. But there they are, the zeros of the zeta function. The zeros of the derivative of the characteristic polynomial. If we have n equals 60, so a larger matrix, again, the eigenvalues of the matrix are the blue dots, and the zeros of the derivative of the characteristic polynomial are the green dots. And we see the same phenomenon as we saw with the zeros of the zeta function, where, maybe here, like if we get two eigenvalues that are very close together, that's when the zero of the derivative of the characteristic polynomial sneaks up against the unit circle in exactly the same way as the derivatives of zeta got up against the half line when you had two zeros of zeta very close together. So we see same sort of distribution going on here between zeros of the derivative of the characteristic polynomial, zeros of the derivative of zeta. And just to convince you even more that the zeros do seem to have the same distribution, this is a plot of essentially the radial distribution of those zeros of the derivative of the characteristic polynomial, right? So this is like on the unit circle moving into the center of the circle, and this is, sort of how many zeros of the derivative you find in each kind of angular ring in the unit circle. So these are results. Francesco is here, and then later a team of people. So this is the picture for random matrix theory. So the radial distribution of zeros of the derivative of the characteristic polynomial. And this is like the equivalent picture for the horizontal distribution of zeros of the derivative of zeta. And the interesting thing is that they certainly have the same shape, right? They both have this funny peak at this point, and they have approximately the same kind of shape. So this is at least convincing that the distribution of the zeros of the derivative of the characteristic polynomial do seem to show the same sort of behavior as the zeros of the derivative of the zeta function.
Is that noun or the asymptotic?
I would refer that to Francesco.
Yes. It's a fairly easy calculation. The difficulty
So if we're convinced that by these pictures that maybe we can use the derivative of the characteristic polynomial to model derivatives of the zeta function, then we go back to the question that the number theorists wanted wanted the answer to, right? So they want derivatives, preferably with a non-integer exponent of the zeta function averaged over some interval on the critical line. And so that's the quantity that we'd like to calculate, the number theorists would like to calculate. And so the equivalent quantity in random matrix theory that we think maybe is an easier calculation and could shed some light on the number theory case would be this calculation here. So the derivative of the characteristic polynomial at some value of s, maybe just inside the unit circle, raised to some power that we would like to be non-integer, and then averaging over un. So unfortunately, I'm not going to conclude this talk by telling you that we've calculated this quantity, because we can't do that yet. But it has motivated a whole lot of other results that we've had a lot of fun doing, and so that's what I get to tell you about. But they're all motivated with the aim of ending up with something like this. So the only result in this line that anyone has, like trying to get a non-integer v, is this one. So this is Brian Wynn, and he got v equals to 1. Now you may think that v equals to 1 doesn't look a lot like a non-integer, but in fact the only time when these calculations are even tractable is when it's an even integer in the exponent. So Brian even getting 1 is an approach to v being non-integer, like a non-trivial approach to v being non-integer. But that's the best that anyone can do at the moment. But it's what we're trying to do. So it's what motivates our calculations. So I'll tell you some of the things we can do, rather than telling you what we can't do. So we can calculate averages like this. So looking at averages of the derivative of the characteristic polynomial, along with some copies of the characteristic polynomial itself for various exponents. And there's been a whole range of results. Many of these people are here. I hope I haven't left anyone out, along this line. So yeah, and this leads to very nice calculations. So that's an average over un of the characteristic polynomial and its derivative. So we can do calculations like that. We can do calculations like this. So here we have the logarithmic derivative of the characteristic polynomial, which could also be useful because it has the same zeros as the derivative of the characteristic polynomial. It just has some poles as well from the characteristic polynomial in the denominator, which could mess things up. But nonetheless, it's potentially a useful calculation. So we can do calculations with the logarithmic derivative of the characteristic polynomial. Unfortunately, k is still an integer, and some of these results are asymptotic for large n, large matrix size. Some of them are exact. What else can we do? So we can also, so there was a group of people looked at higher derivatives, so they can take the second derivative of the characteristic polynomial. Sometimes, so some number theoretical functions called L functions, which are very similar to the zeta function, have zero statistics that look like other classical compact groups, so not necessarily un, but this is the group of 2n by 2n orthogonal matrices with determinant 1. So that's also relevant in number theory, averages over this kind of group. Sadly, k is still an integer. A previous graduate student of mine was looking at quantities like this. So again, averaged over SO2n. Here, the exponent on the characteristic polynomial is a non-integer, but sadly, the exponent on the derivative, which is really what we'd like to be a non-integer, is just 1. So these are the kind of calculations we can carry out. What's that? Oh yes, and the last one. So this is what Amelia's working on, who's here in the front row. So again, a logarithmic derivative averaged over one of the classical compact groups. But again, so far, k is still an integer. Although talk to Amelia in a few years' time, and maybe k will no longer be an integer. Okay, so let me just tell you, I started off with these determinants, which I love it when we can, like, our calculation coalesces into some beautifully structured determinant. So let me return to that for just the last few minutes that I have left, just to tell you how we end up with a determinant when we do this kind of calculation. So let's take this calculation for example, because it's kind of the easiest to write down, the least messy maybe. So we're averaging the characteristic polynomial, the logarithmic derivative of the characteristic polynomial, in this case over SO2n. But it turns out that all these kind of moments calculations can be written in this sort of form. So multiple contour integral, some Vandermonde determinants, which for SO2n usually look like this. So it's a Vandermonde of the squares of your variables and a Vandermonde of the variables themselves. The Vandermonde, remember, is just the product of differences between all pairs of your k variables, and it can be written as a determinant, which has this structure where each variable appears only in one row, and the exponent increases as you go across the columns. So it has this form with some Vandermondes, and then a nice product of functions of your variables which separate. So we get like functions of each of the variables individually, and this is sort of key. And the really key thing is that in this determinant, the jth u, so uj, only appears in the jth row. So we have we want to manipulate something like these Vandermonde factors, and so this is just using the definition of a determinant as a sum over permutations. So that's just writing that determinant in that sum over permutation form. So we have permutations which are permutations of the numbers 1 to k, the sign of the permutation, and then these are just the powers of the powers that occur in each of our columns are occurring here. And this is the same thing, expanding this determinant using the permutation sum, where these are now just the powers of u that appear in here. So we have these two sums, but then the thing to remember is that these Vandermondes occur inside an integral, which is otherwise like completely symmetric in all the k u variables. And so one term in this sum here is the product of u1 to the power 0, u2 to the power 1, u3 to the power 2, and so on. That's one of the terms in this permutation sum. And another one would be the same product, but with different u's occurring to different of those exponents. But because we're inside an integral that's symmetric in all the variables, it doesn't matter how we've labeled those variables inside this sum. And so, in effect, we just get k factorial times essentially the first sum instead of this sum over here. So we have just one sum over permutations that looks like this, and we can then bundle that back up into a determinant, which will look like this in this case, and which again has the property that the jth variable appears only in the jth row. Okay, so now we have this in place of our Vandermondes, and so if we kind of stick that back into here, the reason I put arrows and not equal signs is that the whole bunch of coefficients and other mess, which I'm not showing you, but essentially the idea is that we've now replaced the Vandermonde factors with a single determinant, which has the jth variable appearing only in the jth row, and so now we can use properties of determinants to pull the factor with u1 into the first row of our determinant, and the factor with so forth up to uk into the last row of our determinant. And we can also pull the integrals inside the determinant, right? Because the determinant is like linear. And so we end up with a determinant of integrals like this. And this is where all the determinants that I showed you at the beginning come from. You have various functions f. Say if f was the exponential, right, e to the minus u, then this is basically a gamma function, inverse gamma function or something. And so that's how you get these determinants with the binomial coefficients or the gamma functions in them. So that's the method that you can use for all these various moment calculations. And I still have 5 minutes, I think, so I can actually show you a determinant calculation. So once you get to this form where you have a determinant of, say, binomial coefficients, then you need a trick, right? And in each case, it's usually a different trick that you need to be able to evaluate these. So this is Amelia's trick for evaluating this. This was one of the, this is the determinant you get from this calculation, yeah? When you want to calculate the logarithmic derivative of the characteristic polynomial over SO2n. You end up with a determinant like this, and now you want to evaluate this determinant. So the first step is to note that we have that relation, from Pascal's triangle, and that says that we can reduce this difference of binomial coefficients to this one here. And if we look at our determinant, we can see that if we subtract, say, this element from that element, then that's this subtraction here. And we can end up by reducing the top and the bottom index by 1 in each case. So, for example, we could work with the bottom row and subtract off the row above it, and use this relation. So bottom row subtracting the one above it, and then we get this, and that changes, it reduces the indices in the, I think I've written that one wrong. It reduces the indices in the top and the bottom of the binomial coefficients by 1 in each case. And then we can move up and do the same thing to each row in our determinant, and we are slowly moving down all the indices in our binomial coefficients. We're going to leave the top one where it is, but start reducing all the lower rows. And so we eventually get to this form here. So this is just, it's just adding rows to other rows, so we haven't changed the determinant. So we get something like this. Now, the bottom row is just a row of 1s, right? Because they're all something choose 0. The next row up, in the jth column, we have something that looks like this. So 2j minus 1 choose 1. That's what each of these looks like, where j is the column index. And so that is just 2j minus 1, right? We can get rid of the 1 because we have a 1 in the bottom row here in every column, so we can just add the bottom row to get rid of that 1. We can pull out a 2, right? That's the 2 here, because it's going to appear in every one of these entries in the second to last row. Pull out the 2, and so we just get left with j, where j is the column index in that row there, right? So we're simplifying our determinant. Okay, and so we continue this process. So we have 1s in the bottom row, we have j in the second to bottom row, and then if we look at this row here, that's 2j minus 1 choose 2, where j is the column index, which is just a quadratic in j, the column index. And again, we can get rid of the constant term by adding some multiple of the bottom row. We can get rid of the linear term by adding some multiple of the next row down. And so we end up with essentially j squared, right? We pull out some factors of 2, end up with a j squared. And you just repeat this process until you get this here. So you have some coefficients out in front, and then this is like a Vandermonde in the numbers 1 to k, which you can evaluate. This is all the differences between the numbers 1 to k. And so it evaluates it like neatly evaluates to this nice power of 2. And so, yeah. And so you can take these moment calculations and kind of turn them into a really beautifully structured determinant that then you could then hope to evaluate using some tricks like this. So yeah, so my conclusion is that we haven't managed to answer the question that the number theorists would like to have answered, but that we're working on it. Thank you.
Thank you very much. So now we go to questions, and I was asked from, this is filmed, so that I hand around this microphone so also that the questions can be recorded. Maybe during the talks, the speaker might want to repeat the question because...
Yes, I have a short comment that for real eigenvalues, models where you have a Vandermonde of some powers times an ordinary Vandermonde have been studied quite extensively. These are called Mutale-Borodin. And if you look for power 2, there's a paper by Sommers and Zirnbauer, this relates to bosons. So this can be interesting. I have another short question. Have people looked at the statistics of the zeros of zeta prime in the complex half plane? So not just doing averages, but let's say two-point function or repulsion of these zeros in the complex plane. I
haven't, no. But I get, yeah, I mean, yeah. So it would be interesting to do that and to compare with the equivalent thing for the derivative of the characteristic polynomial. But I think the only results on the distribution are Francesco's and his friends.
Yeah, so when you have this calculation which at first holds for a positive integer k, what's nice, I guess, is you can see at the end that when you've computed the determinant that actually you have an expression which you could actually continue in some, perhaps. I wonder if you expect that to hold for more general values of k.
Well, so clearly that's what we'd like, right? To be able to somehow continue to non-integer values of k. But yes, we haven't
It's difficult
got to that stage yet.
test.
Yeah.
So there's one question in the front row.
So in the SO2 case, do you get any link to pen levé?
I don't think anyone has shown that yet. I may not be remembering things. Yeah, so in the unitary case, as you know very well, yeah, these kind of calculations linked to solutions of Hennenfent equations. But I can't think of a result right now for SO2n.
Sorry. No, the result you mentioned for k equal 1, I mean, so does it use different techniques? You mentioned the result for k equal...
For Brian Wynn?
Yeah.
Yeah. It's, yeah, certainly different to these techniques.
Doesn't fit this... So you don't recover k equal 1 from this, this construction?
We don't know.
The number you have there, the very last number, 2 to the power k choose 2, also happens to be the number of Aztec diamonds of size k minus 1, which can be enumerated as a determinant in terms of non-intersecting Schroeder paths.
Right,
paths.
sorry, which number?
2 to the k choose 2.
Oh, right,
Is also a determinant in terms of Schroeder paths, which are also related to some moments of Laurent polynomials of, I forget exactly what. Have you looked at the connection? There's probably, my guess would be that there might be something going on.
Yeah, I haven't looked at the connection. There probably is, since random matrix theory obviously is applicable in many cases. The power k choose 2 is what you often get when you're dealing with the group SO2n. So when you do these kind of moment calculations, so maybe there's a connection between that group and the situation you're talking about.
Are there any further questions? No, I don't see any. So let's thank the speaker again for the discussion. And we continue just in 2 minutes. So